Welcome to Chapter 4, Statistics. We're going to be covering 4.1 to 4.3 of the ninth edition of the Harris Quantitative Chemical Analysis textbook. So let's get started. On 4.1, they talk about Gaussian distribution. Essentially, Gaussian distribution is a normal curve. So Gaussian distribution, normal curve, they're all the same thing. And how this Gaussian distribution is produced. So basically, this Gaussian distribution or normal curve is produced after the replicate measurement values has been put into a graph. So what I mean is like all of the data, those quantitative data that you got from your experiment. So those numbers that you got from your experiment, after you put them into a graph, it will look like this bell-shaped curve right here. Okay, so in this bell-shaped curve, you're always going to have a mean. Mean, in this case, it's going to be right here at the dead center. And then the width of the distribution pretty much tells you the standard deviation. Right here, this measurement of the width being the standard deviation of that normal distribution. So mean, center, standard deviation measures the width of that distribution. In every normal curve, there's always going to be the two. Alright, so let's gonna talk about the math now. So the math, the mean is kind of pretty simple. Mean is just what we call as an average. In this case, the sigma right here, this one tells you that you're gonna add every number that you have on your data set. Okay, and then you're gonna divide that by how many are there. So that's just basically the mean. And then, sorry, I'm just gonna put add together. And then standard deviation is just going to measure you how closely that data number that you got from that data number into your mean. So let's break it down first. So this is sigma, so that means we're going to add it together, okay? So that's what sigma means. Xi in here tells you the individual values in your data set. So you're going to do it one number at a time. So the first number minus the mean, that's what x naught is. It's here. And then you're going to square it. And then you're going to do it with the second number, right? Minus the mean. And then you're going to square it. And then you're going to do it on the third one, minus the mean. And then the second number, and so on and so forth. That's kind of the idea. And then you're going to divide that by n minus 1. So n in here is what is known as a sample size. That tells you how many are in there in that sample. And then at the end, you're just going to square it everything up. So that's kind of the math behind it. And all you need to know for the standard deviation is that if the width, right, of that measurement, of that distribution is closer to the mean, that means it's more precise. However, the farther the width is from the mean of that distribution, that means it's going to be not as accurate that it seems like. So in every bell-shaped curve, which is known as a normal curve or Gaussian distribution, you're going to have this empirical rule. And this empirical rule basically tells you how many are there falls within a certain standard deviation. So if it's one standard deviation, approximately 68% of the observation falls within that thing. If it's a 2 standard deviation, approximately 95% of the observation is going to fall in there. If it's 3 standard deviation, approximately 99.7% of the observation is going to fall in there. So In every normal curve, you're gonna remember this. It's gonna be 68, 95, 99.7. 68, once again, one standard deviation is gonna fall in there. 95 is 2. 99.7 is 3 standard deviation. So you just gotta remember this all the time. Okay, some definitions that you need to know. On the formula on your standard deviation, this n-1 is what is known as a degree of freedom. So I'm going to explain to you what that means, but that's what it is pretty much in mathematical sense. And then the relationship between variance, okay, and standard deviation is that standard deviation, if you square it, so s squared, that means it's a variance, okay? And sometimes if you want to express standard deviation as a percentage, you can express it through this, known as coefficient of variation. So coefficient of variation has two things in here. The first one is the 100, as you see here, and then you have the x, then the x naught. So the s in here is your standard deviation, and then right here is your mean. Okay. And then also some things that you need to know. In a normal distribution, there's going to be z-score. So a z-score in here gives you an idea how far the a data point is. So basically, it's just a measure of how many standard deviations below or above the population mean a raw score is. And then degrees of freedom of an estimate, remember that's the n-1, is the number of independent pieces of information that went into calculating the estimate. So z-score in mathematical sense, you can always break it down into this formula. The way I kind of remember it is that x in here would be your measured one. This is what you obtained from your experiment, and then this thing right here is called the population mean. This is the mean that you got probably from after you did the normal distribution. So this is usually what's on the dead center. Sometimes it's going to be given to you, sometimes it's not. Then divided that by your standard deviation. This is usually population standard deviation. So z-score is just going to be like basically how far is that measured score is with relates to its mean using under its standard deviation. In here is a z-table, and it's important that you need to know this. So in a z-table, what this means is that after calculated your z-score, so first calculate your z-score, and after you calculate the z-score, you're going to look into your table. So the thing is, you're going to look into here on the ZA category, and pretty much all you need to know in here is this Z and then area. I'm just showing it to you because this is the thing that you're gonna see in your exam, probably on ACS final. These ones right here, okay? So what you're gonna do is after you calculate your Z-score, it's gonna give you a value, for example, 2.9 for some weird reason. And then in here, so after you do that, you're gonna look into the Z category and look at 2.9. So this is 2.9, right? And then after you look at 2.9, you're gonna go here into area. So in the area, that's the one that is gonna be important right here, the area, okay? Because that tells you that tells you the probability, right? That it's gonna be within that, I guess that area, right? Okay, so just know that. Okay, that's how you interpret it. Alright, so we're gonna do a lesson or more than case test. So what they did in here is that we're gonna do it using the problem. So suppose the manufacturer of the bulb used for figure 4.1 offers to replace free of charge any bulb that burns out in less than 600 hours. If she plans to sell 1,000,000 bulbs, how many extra bulbs should she keep as a replacement? So I know we're not given the figure from 4.1, but we know that the x naught, meaning what's on that dead center of that normal curve, is 845.2 hours, and the standard deviation being 94.2 hours. And then z-score, remember, I just do it like this, x over this. So usually the x in here is what's given to you. So that's 600. And the population mean is basically the dead center of your Gaussian curve. So that's 845.2 according to this problem. And then the standard deviation is 94.2, so you're just essentially plugging in. So after that, you're going to get a z-score of negative 2.60. If you look at negative 2.60 on this table, so I'm going to read 0, 1.3, 5, 2.6, perfect, it's right here. And remember, I don't need the y, so I'm just reading right here. And I saw 0.4593. Remember, 0.4593 is just if it's within that 600 hours. If it's less than 600 hours, that means you're going to subtract that by the area from the left of the negative infinity of that value to the mean value. So that's really important because that's the less than. So let me draw the curve to kind of like, I guess, help you understand it. What they're telling you, is this. Draw it. Okay, so what they're telling you is not right here at the dead center. If it's at the dead center, that means it's going to be that 0.454953. That's not the problem. They're asking you what's down here. I'm going to color it differently. Oops. Okay, so this is what they're asking you, okay, on this problem. So what you're going to do actually in here is you're going to subtract about half of it in there into this 4953 to get the final answer, which is this. So that means actually the area of it is really, really small. This 0.47 of it are expected to fail in then 600 hours. Okay. Some different situations that are going to occur on a z-score that I think everyone should know is that between 0 and any number, just look up the area in the table. If you have between two positives or between two negatives, look up both areas in the table and subtract the smaller area from the larger area. Between a negative and a positive, just look it up and then add them together. Less than a negative or greater than a positive, look up the area in the table and subtract from 0.5 thousand. Okay. And then you're going to do the same thing for greater than a negative or less than positive. But instead of subtract, we're going to add this time. So look up in the area in the table and add to 0.5000. This one is, I believe, 4.2. And they're talking about F-test. F-test tells us if the standard deviations from the two sets of data are statistically different. So in here, all you need in here is the standard deviation of one part and then the other part. So we can run an F-test on it. Usually, to do this, you're going to put the larger standard deviation in the numerator, so the larger one. So I'm going to put it here. So larger stdev and smaller stdev right here at the bottom. Then what you're going to do is you're going to square it, okay? And then after you do that, right, you're going to look at the F calculated and F table. So you're going to have a table similar to z-score in which you're going to look it up to determine if it's significant or not. So what they did here is that after we calculated the F, we're going to give this value. However, on table 4.3, I don't have that one, the F table is at 3.6. And since we know the F calculated, right, is less than F table, that means they're not statistically different from one another at a percent confidence interval. And that's the same thing with FCalc, or that's not the same thing, but if it's significantly different, that means your calculated one is less than the F value that you got from your table. So that's one way to know. And then 4.3, students tease statistical tool used most frequently to express confidence intervals and to compare results from different experiments. You're going to use it to characterize or make judgments about the data. Tells that use of the student's t-distribution for confidence intervals, comparing a measured result with a known value, comparing replicate measurements, comparison of means of two sets of data. Usually in a confidence interval, you're going to have two things. The first one is your mean, and then this part right here, which you're kind of a bit uncertain of. So the t in here is actually the t value that you got from your table, and then the s is the standard deviation, and then the n is just the sample size that you square, okay? And this is the student's t, and as you can see, there is a different t value at a different confidence level. And what you're going to do is that, you're going to read you're going to figure out how many are there in a data set, because you need to figure out obviously the degrees of freedom. So remember, degrees of freedom, it's always going to be n minus 1. So that's going to be n minus 1 right here. And then what you're going to do, depending on what's given to your problem, you're going to read at your appropriate confidence level. So let's say it's at 95% and we have 8. Okay, remember, we have 8 of them. So in degrees of freedom, we don't have 8 of them. We have 7 of them. Okay. Then we're going to read at the 95, and we're going to get 2.365% confidence level. So these are some of the problems. So The carbohydrate content of glycoprotein is found to be 12.6, 11.9, 13.0, 12.7, and 12.5 weight percent. So that means it's a gram carbohydrate per 100 gram of glycoprotein. And replicate analysis. Find the 50% confidence interval for the carbohydrate content. So the first thing that you need to do, what I would like to do is break down the formula for confidence interval. We know in a confidence interval, it is consists of the mean and some other stuff too, like the TS. Ooh. I don't know, it's not working. It's consisted of this right here. Okay, and then the T, and then the S, and then this. Okay, so what that means is that the U is X, which is your mean, so you need to get the mean, and they got the mean as a 12.54, so that one is just the extra one from chapter 3 to account for the error. And then on the next part we have TS. So what the heck is T? T in here would be first to know how many are there in a data set. So you have 1, 2, 3, 4, 5. So there's 5. So there's 5. So that means in a T table, we're going to have, I would like to put it as this. So in a T table, I need to have degrees of freedom being 4. And I'm looking at a confidence interval of 50%. So for 50%. Okay, so for then 50% would be here, right? This 0.741. So it's going to be 0.741 as we determine on the table. And then what the heck is this S? S is the standard deviation. So once again, usually what you're just going to be doing is put everything on the calculator, get the 1 bar summary of it so you can get the sample mean and you can get the standard deviation. So, and then after that, you're just gonna, at the bottom of this TS, gonna square the N. So N in here is 5 because that's how many are there in the data set. And then you're just gonna square it. So after you do that, what I'd like to do is deal with this first chunk, which ends up to be 0.13. And then you're just gonna add and subtract that. And that means 12.54 plus 0.13, it's going to fall in that one. And then it's also going to be 12.54 minus 0.13 in this part. So it's between this value and that value. That's what confidence interval is within a certain percent confidence. Okay, so this is, and what that means is that 50% chance that the true values lies in this interval. That's why the higher your confidence interval, that means the better that a certain value is, right, that it's going to fall into. So just remember that.